Test 1, 2, 3.
Hello, hello. It's 6:30 and I think we're ready to start. This is the regular monthly meeting of the Tucson Amateur Astronomy Association. We meet the first Friday of the month at the auditorium at Stewart Observatory at the campus of the University of Arizona. Tonight we have got members in the audience here in the auditorium. We also have members who are joining us by Zoom, and we have got guests that are joining us on social media. So welcome everyone. We have got a number of pieces to our program tonight, but we like to start with a little bit of literature. David Levy, are you with us this evening?
Yes, I am.
David Levy says, yes, I am over. Yes, David Levy says,
Yes,
I don't know if we can hear them though, but.
David, you might be, is he muted?
Or we would need to, you might be.
David, we see that you're on. Can you unmute?
Okay, I'm unmuted. Is that better?
He's unmuted, but the problem is I don't think that the audio is coming through the system. Yeah, well, we can change that. I didn't realize that would be.
Just a moment, David. We're looking at our audio-visual connections here.
Can you hear me now?
Give us just a moment
No, I
and
think
we'll
it's the
see if
other
we can't make you
Yeah. Yep. And just change it back
live
to
and your audio come through.
Class PC. Yep, right there. And I think then, okay, now
Our
hopefully.
crack technical staff is working. And okay, David, try now. See if we can hear you.
Okay, can you hear me now?
Yes.
Yes, yes, yes.
Great, okay. I want to add my welcome to this wonderful monthly meeting of the TAAA. And I'm very much looking forward to Kevin's interpretation of what the James Webb has done over the last 4 years, which I know has been quite a bit, and it'll be good to hear, to get a summary and interpretation of what has happened with it. But it also brings me back to an observer who was very, very popular and very, very famous at the end of the 19th century, well into the 20th century. And that observer was Edwin Emerson Barnard. And the second part of the meeting is going to involve former President Tim Hunter and his second book about Barnard. I think Tim should be congratulated that he has taken the trouble to do 2 books about Barnard. And I was really very honored that he's going to be a part of the meeting tonight. I never knew Barnard, much as I would have liked to. Very complicated man, one of the greatest observers who ever lived. But I did know someone who did know Barnard, and that was Leslie Peltier. And Barnard asked Leslie to any comet discovery that he might have made to send it to him, as well as to the official announcement place. And so I got to know Leslie very well in future, in the life that Leslie had during most of the 20th century. For my quotation today, in honor of the new book, we're going to go to actually a singer, Don McLean. In 1971, he wrote a very famous song based on Van Gogh's painting Starry Night. And Van Gogh had written to his brother that a starry sky is something I should like to try to do. And he wrote that very modestly, because he would have to do the Starry Night from the window of the insane asylum that he was living in at the time. And little did he know, little did anybody know at the time, that the Starry Night would become one of the truly great works of Western art. And Don McLean's song that I'd like to quote for you now is called Vincent. And when no hope was left inside, on that starry, starry night, you took your life as lovers often do. But I could have told you, Vincent, this world was never meant for one as beautiful as you. And on that happy, sad note, I'd like to give it back to Ed. Thank you.
Thank you. Thank you, David. A new side of David Levy that we haven't heard before. All right, thank you much. Okay. I just want to make sure that everyone got a raffle ticket on their way in tonight. If you didn't, oh, there you go. Top of the stairs. Very important. You'll see why later on this evening. Important part of the night. Okay. Let's get to the main body, because I know that everyone loves this telescope. Tonight we have joining us Dr. Kevin Hainline, an astronomer here at the U of A, and he studies early galaxies. And if you know anything about the Webb, it is a gem when looking way back in time. And Dr. Hainline is going to tell us how it's doing and whether it's doing a sufficient job in that area for him. Dr. Hainline, please.
Thank you. Hi, everybody. How y'all doing? Good? This is exciting. Thank you for coming out on a holiday weekend. It's July 3rd, and you could be getting ready for barbecues or whatever, but instead you're here listening to an astronomer talk about something that I think is pretty exciting. I was just joking beforehand. I have given talks. I've been at Stewart Observatory for over 10 years now. And when I first started giving these talks, it was in the lead up to the launch of this telescope, when it was still in parts. And I would give talks that was like, okay, get ready for this telescope. This telescope's really exciting. And I'm really happy that it's successful, because otherwise I would not be an astronomer anymore, and I would not be allowed to give talks anymore. So it's very, very cool. I'm an associate research professor here at the University of Arizona. My office is within a 5-minute walk of here. The building is locked because it's a holiday weekend, but if you were to walk into the building, the main entrance, you'd pass my window. I'm right there on the ground floor. And I just want to start this talk by saying it's kind of amazing how fast time goes. It's been 4 years since the first JWST public images, which is really, really exciting. And that was like 4 years to like in a couple weeks. So like it was like July 15th, I think, of 2022. And so this is like 4 years of public JWST data. Now, I say public JWST data because JWST was taking data for about 6 months before the public data, because it launched in December. It took about a month to get out to its spot 1 million miles away. And during the time as it was going out and we were turning on the instruments and stuff, we were starting to go out, myself included, and members of the JWST NIRCam team and the MIRI team go out to Space Telescope Science Institute, which is outside of Johns Hopkins University in Baltimore. And we were turning the instruments on, taking our calibration data, doing all of the tests and stuff. And that data is, in fact, public now. If you want to go sift through calibration data, it's not very pretty. The telescope, in many cases, from the data wasn't focused. But then after 6 months of us making sure the telescope worked, Space Telescope secretly went and took images of these very famous parts of the sky. And I say secretly because members of the team on the camera that the images were being taken were not allowed to know. This is such a top secret thing. Unfortunately, those members of the team, myself included, had to actually be on console when the images were taken. So we had to take and put the, okay, well, here's what the RA deck is of the objects we're looking at. We just couldn't look at the data when it came down, but I knew all of the images where they were being pointed to because I was sitting on console using the camera itself to take those images. I just couldn't look at the data afterwards. It was a whole secret thing. They went to their secret scientists to do the data reduction, and then the data was all revealed to the public on a Monday morning. And it was a really wonderful Monday morning. There was a big press conference that the president, at the time, President Biden, wanted to come in and actually show off the first images. And it was a very exciting day because I, for the first time, could see what these images were that we were looking at. So it's been 4 years since this very famous image, the cosmic cliffs. It's like one of the most famous JWST images. Marcia Ricci, who is the PI, the primary investigator of NIRCam, she's a professor here. She has this wonderful jacket that she wears to all of her big fancy award ceremonies that has the cosmic cliffs on it. I think it's a gorgeous image. It's been 4 years since Stephan's quintet. Oh man, why? Yeah, I see. I'm going to click OK, and we're going to do that, and I'm going to come back so that I have this. Great. Stephan's quintet, which is a group of these 1, 2, 3, 4 galaxies, and this is the second most famous image of this. Do you guys know what the first most famous image from this is? It's in the movie It's a Wonderful Life. At the very beginning, all of the angels are talking from Stephan's quintet. That was taken at the time with the Wilson Observatory 100-inch, and it's like an amazing thing to go from that, which at the time was one of the biggest telescopes in the world, to this, one of the most impressive images. I absolutely love this. It's been 4 years since the Southern Ring Nebula image. This is this wonderful, wonderful image where I really appreciated this because when they were talking to the scientists, they were really excited. There was a scientist who was like, we don't actually know what this is. We think it's part of the Ring Nebula. Like he's being interviewed live, as part of this. And I knew what that was. That's a galaxy behind the thing. This thing is a galaxy machine. And it's just, why would you put this big red thing in front of all the beautiful galaxies? See, there's a bunch of little galaxies that are back in the behind this. Here's another one. And we'll talk about that later on. But this is a beautiful end product of a star. It's been 4 years since this Southern Massive Cluster Survey 0723, this image, which was called at the time JWST's Deep Field. This is the Deep Field. This represents about 12 hours of observation. And at the time, because of the size of JWST, it was, in fact, the deepest image humans had ever taken, especially at this wavelength range. But I'm getting ahead of myself. Maybe you are in this room as a Tucson Amateur Astronomy Association member or friend of the TAA, and you're wondering, what is he talking about? What's JWST? What an exciting thing if that's the case. Because we want to know what it's been doing the last 4 years. But let's start with, this is JWST. It is a space telescope that is the successor to the Hubble Space Telescope. Successor is kind of the wrong term because they both work together, as long as Hubble still has funding to stay up there. But it's essentially, it is NASA's next generation space telescope. And in fact, that's what it was originally called, the next generation space telescope, until they decided to name after old John Waters up here. It has a mirror that is about 6.5 meters in length, so 21 meters. We'll talk about that in a second. And it floats 1 million miles away in a spot called L2, Lagrange point 2. The mirror, each one of these mirror segments is like this big. I was working on the instruments when they were assembling the mirror, and I could look through this window in the room that had a very annoying thing that said "Do not take pictures" on it. But I would look through as they were to take every one of the mirrors and prep them, make sure that they were ready to go and be put onto the back plane of the mirror, which is really big, cool. So that each one of them is about this big around. They're gold plated. The amount of gold that would go on this mirror was about a golf ball's worth of gold. Gold reflects infrared light well. We'll talk about infrared light. And it sits on top of this beautiful sun shield. So you have, I don't know why this does this sometimes. You have primary mirror, a secondary mirror, because the light bounces off the primary, hits the secondary, and then goes into this black box, which is called the aft optic subsystem, to all of the cameras back here. And there are 4 of them. Again, we'll talk about that. And then it sits on this big silver sun shield, which keeps it very cold. It needs to be incredibly cold because of the wavelength of light which it's sensitive to. So let me give you an idea of how big it is. Here is myself. Here's the Hubble mirror. And here's Shaquille O'Neal, so a little taller than me. And he's about a Hubble size. So you can see that it's a number of Hubbles tall. It's also, 4 refrigerators tall. It's a little bit taller than an adult giraffe. And if you think in terms of R2-D2s, it's about 6 R2-D2s tall. But like this, I made a video before JWST launched where this was one of the screenshots from the video that I was very proud of, because and I have gone to talks by other people where they've used this slide. And it's really weird to see myself as their little comparison down there. The reason that I am here, and the reason why JWST, one of the nice reasons why JWST is as successful as it is because of this box right here. This box is called NIRCam, the Near Infrared Camera, and it is the primary imager on JWST. I'm going to show data from a lot of different instruments on board the telescope, but many of the images, which is really what is the dazzling part. I apologize to people who are really big into spectroscopy in this room, but here we have editors from magazines in this room, and they can tell you that no one buys magazines to look at spectra. They buy magazines, they use the internet to look at images, and this is the imager. So this is the camera that is taking a lot of the images that I showed you, and I will show you. It's actually 2 identical cameras sandwiched together. You can see that every part down here is mirrored with a part above it. This box is that box, this box is that box, and these are called Module A and Module B. And they're a redundant system. In case Module A breaks, we still have Module B or vice versa, but they work together in tandem to take big rectangular images of the sky. Also, the fact that there's a drum here and a drum here, those are the 2 different filter wheels for the fact that NIRCam also takes images at one wavelength range and at another wavelength range, long and short wavelengths at the same time, which makes this instrument incredibly efficient. It's got a big field of view, not enormous compared with other cameras, but for how sensitive and how big the mirror is, it's incredibly big. And compared to Hubble, it's incredibly big. But it also allows you to take a bunch of 2 different filters at the same time, which means it's very efficient in its wavelength coverage. NIRCam is an instrument that I was hired to come work on and be on the science team with. I helped shepherd this throughout its entire existence, and when it was on Sky, taking some of these images, and I am an expert in the functionality of this wonderful machine here, and its fun, weird quirks and nuances, as we'll get later on in the talk. This right here is another University of Arizona assisted instrument. This is the mid-infrared instrument. I will be showing you some images that have mid-infrared instrument or MIRI coverage a little later also. And the US science lead is Marcia Reiki, who's the PI of NIRCam. Her husband, George Reiki, he's the US science lead for MIRI. So they are kind of a dynamic duo of JWST instruments. When I asked Marcia before the launch of the telescope what instrument she was most excited about, and again, she's the primary investigator of NIRCam. It's her life's work. She, without hesitation, said, "Oh, MIRI," because MIRI is the instrument that will do things that, like in a wavelength range in a regime that we've never been able to do before. NIRCam, we've had other instruments that kind of operate in the same wavelength range. Hubble has an instrument that goes about halfway into what NIRCam can do. But MIRI, which operates at longer wavelengths, is like a completely new frontier in terms of science. It's a very, very exciting instrument. So to understand when I say the infrared, or why I'm talking about mid-infrared, near-infrared, what that means, here's light. This is our little light refresher, where we have light at all wavelengths here represented in this. And some people are always confused because they don't think of X-rays as light, but it is. When you go to a dentist's office or a doctor's office and have an X-ray taken of you, it's just like a fancy flashlight that is incredibly dangerous. Because as you get to this left, you're getting to very energetic light, gamma rays, which is what makes you into the Hulk, X-rays, which is a light that can go actually through your body except your bones. Ultraviolet, which is dangerous enough that you wear creams on your skin here in Tucson to protect you from the ultraviolet light. And then there's this little tiny, tiny sliver, which I've come out here, because that's all of the light our eyes are sensitive to. And then as you go to longer wavelengths, you get infrared at less energy, and then radio waves. So again, my cell phone, which emits radio waves, it detects radio waves, it's just a fancy flashlight, a radio flashlight. We have so much that we communicate and can understand about the universe and about the natural world just through observations of light. Electromagnetic rays and radiation is like fundamentally important to human understanding and science. But our eyes are just like only privy to this tiny, tiny little wavelength range right here, and that's because the sun emits most of its light in this wavelength range. But if you were to keep going to longer colors, to redder and redder colors, you'd get in the infrared. And the infrared, we don't have like fancy names for those colors. We don't call them like flurple or glow orange or something like that. We just call them near-infrared, mid-infrared light, and often they are associated with the wavelength of it. Near-infrared being close to the optical, so a little bit redder than we could see, and then mid-infrared and far-infrared continue going to longer and longer wavelengths. So here is our diagram where I'm showing that same rainbow of what we can see with our eyes and where JWST can see. 3 of the instruments on board JWST, NIRCam, which I just talked about, NIRSpec, which is a spectrograph, I'll show a little bit of spectra, and then NIRIS, which I will actually not show much of, but it's a Canadian instrument that kind of does a little bit of what both of these two do. They operate, and you can tell from the NI and all this, in the near infrared, so just a little bit beyond the red, and then MIRI picks up where they go, they leave off and moves into the mid-infrared. And so these 4 instruments work in tandem. And in fact, one of the amazing things about JWST is that it's really only limited by the hard drive and ability to send data down. If we had an enormous hard drive, and we had a cord that was going from 1 million miles away to Earth all the time, we could just open up all the instruments and take data constantly. But the thing is we're limited by the bandwidth that the telescope can support. So, but we have the ability to take images where we'll be observing with NIRSpec, and then we can turn the camera on at the same time. They're not looking at the exact same thing in the sky. It's a little bit off, but you can be very clever about I want to observe this and take a picture here, and then I'll turn the telescope or wait until the telescope can go 180 degrees, and then I'll do the other way, right? So you can actually be very clever about using these instruments in tandem, which makes it even more efficient. And that matters because it's a space telescope that is limited in its lifetime by the amount of fuel that it has. And at some point, it will run out of fuel, and it will just float off into space, which is going to be very sad for me. But that means that each year there's a call for proposals, and scientists are just climbing over each other to try and get data on this telescope because it's such a successful telescope and it works so well that, and we are limited in the amount of time that we have to give to the scientific community. And so if you can find ways to be efficient in your program, to be like, oh, actually, I'll do this in parallel, you will actually show that, like the people who choose what telescope proposals to get accepted, you'll show them, and this one actually is kind of an exciting one because you can do a lot of stuff in a small amount of time efficiently. So let's talk about some of what we can do with this telescope. I just showed you stuff that you probably already know, some of you in the room, but I want to just talk about why we build a telescope like this. So this is one of the reasons why we build a telescope like this. This is Pismis 24. It's a very similar star-forming region to what I showed you at the beginning, the cosmic cliffs, which are in the nebula Carina. But this here is a region of sky where you are seeing like stars after they've been born. So this is kind of like I don't know, stellar junior high. And what you're seeing is the edge of one of these star-forming regions. When stars are born, they're born in giant gas clouds. The gas collapses due to gravity. There are places where it's more dense, and they form these new baby stars. And when babies, human babies, cry really loudly, we attend to them. When baby stars cry really loudly, all of the gas runs away. Like the light is so powerful for baby stars, it pushes the gas away. Thank goodness that human babies don't do this as well. They just and so what you do is you get these groups of young baby stars making so much light, energetic light, it's pushing the gas away and making a big bubble. And if we looked at the edge of one of those bubbles, you'd see this. And these little fingers, gosh, I really am frustrated by how pixelated this looks with this screen. It's not that way on my computer. And for those of you watching at home, you're getting a nicer experience in terms of seeing this at a better quality. This projector is not the best. But these fingers are areas where it is denser. The gas is denser. And when you have a lot of gas and a lot of dust, it makes it difficult to see through to see the young baby stars. And what we're seeing here is actually more stars than we'd see in this region with Hubble, because we're able to see through a lot of that dust because we're looking in the infrared. And this is a machine, JWST, in many cases to help us understand star formation in a way we've never been able to. Because instead of us being limited by the fact that, well, we can see some of the regions, but not the dustiest, most clumpy regions where the baby stars are, we can actually start to see that using this telescope. If I zoom out, I can show you another star-forming region that's a little bit farther away. There's a star-forming region in a nearby galaxy. This is maybe my favorite image from the first couple of years of JWST. I absolutely love this. This is NGC 602, and this is one of these regions I showed you. You're seeing the bubble being inflated by the baby stars. This is the bubble, right? If I were to zoom in, or if we had the, this is thousands of times farther away, you'd still see these fingers, just like I showed you in the last one, which is a lot closer. But this is in a nearby galaxy. It's in the Large Magellanic Cloud, which is one of the two dwarf galaxies that are being eaten in orbit around the Milky Way. And the fact that we can get resolution to actually see how stars are being formed in this galaxy is very exciting. Another aspect of this image that I think is also exciting, beyond the fact that it's just chock full of galaxies all in the background here, is that this region also is we've found some of the farthest, what are called failed stars or brown dwarfs ever seen, have been found in this right here, this image. It's a really exciting thing to show us not how stars are born, but how some stars actually never get big enough to form into a full star. And that is a thing that until JWST, every other brown dwarf that had ever been discovered was within like 300 light years of the Earth. And this one is 100,000 light years. It's really far away. I have it right here. It's 200,000 light years away. Right? So it's a very, very exciting thing that because of the fact that JWST, and why that matters, why it matters that we found that with JWST, is that JWST, because it is sensitive to infrared light, it's going to be able to see through dust. At longer wavelengths, it's going to see cold dust. And it's going to see cold things like brown dwarfs. Brown dwarfs, and I study those as well because I found some that are also very far away, not as far as this, but still very far within the Milky Way. Those ones are so cold that some of them are a little bit colder than my coffee in the morning. Like their surface is a little colder than my coffee, which is absolutely crazy to think about. Here is on the other end of star lifetime, this is a planetary nebula. This is called the Red Spider Nebula right here. Man, these images, it is such a bummer because they look so much. I'm going to have to complain to the department to be like, well, what's going on? You're making me look terrible. The Red Spider Nebula here is a near-cam image, and it's a planetary nebula, which means that it is the end result of a star like our sun. When it dies, it will not die in a supernova. It doesn't have enough stuff. So at a certain point, it will inflate so large that gravitationally it won't be able to hold on to the outer layers, which will kind of puff off. The star's core will get very hot and push the rest of the star's atmosphere out. And you're actually seeing that, in the process here. This blue and these red filamentary structures, those are the outer layers of the star that is puffed off into space. It doesn't puff off equally because it has, at certain other times, puff things off in different places. It's also existing within an interstellar medium that helps to collimate in this and make this beautiful shape. But planetary nebula are very, very exciting. because they teach us about how stars give back their gas and dust to make new generations of stars. So you owe your life to processes like this. Because as people say, we're made of stardust, but as you notice right now, you are not inside of a star, which means that at some point, a star built you. And it didn't build you around the edges. It built you atom by atom in its core. And then the stars died, often with supernova, but in many cases through things like this, giving up some of this outer layer in this atmospheric stuff, which is things like carbon. We'll come back to this idea, but this is why we study these things. And with JWST, we are getting an unprecedented look at the resolution, not the resolution of the projector, the resolution of the telescope, at a resolution we've never had before, and a sensitivity. Here's a really pretty image of another nebula, the Helix Nebula, where we're actually able to kind of zoom in and really, really look and understand the, because like for you, it's very pretty aesthetically, but for astronomers, the colors actually matter. And the colors matter because this is an image taken with multiple filters that have been added together to make a very pretty image. But by looking at all the individual colors and the individual images, you can understand the chemistry. So you can start to see this process that I just said. The reason, it's one thing to say, oh, we're made of stardust. It's another thing to actually watch that going on and seeing the formation of complexity in the atmospheres of these stars after they've died. One thing that I think is really exciting about NIRCam is we've been looking at lots of objects that are hundreds of thousands, thousands of light years away, hundreds of thousands of light years away. But NIRCam is an incredible telescope camera in that we can also take a picture like this. You all are familiar with what this is because you can see this with your eye at night. Not this, like this, but like at night, tonight, right? I think Jupiter's up tonight. I mean, it's cloudy, but like you can see Jupiter with your eye. This telescope that we built has a camera that can see light that is billions of times fainter than the faintest thing you can see with your eye. And yet, we can take a picture of Jupiter. That's insane to me because like it is a very bright object. Light is bouncing from the sun off of this enormous object. You have to be very clever with how you use NIRCam so you don't saturate it. You don't just like, it's like, like if I asked you to take a picture of the sun with your cell phone, your camera would just immediately, couldn't do that, too much light. Jupiter should be the same way, but we can be very clever about how we use subarrays. We don't use the whole camera, use subarrays to take pictures and get images like this. And this is an amazing image because with an infrared telescope, you can see deeper into the atmosphere. You're not just seeing the top of the atmosphere like you would with Hubble, with optical telescopes from the ground. You're seeing deeper into the atmosphere where you're actually seeing some of the chemical makeup of what's going on down below in some of the bands. And then you can also see this red, which is the aurora on Jupiter as well, which is very exciting. I just think it's really amazing that we can take a picture like this. I was stunned. It's a little harder to take. I think we've tried to take pictures of Mars, but you had to be very, very, very clever. Mars is a little bit too bright for NIRCam. But Jupiter's just barely on the edge of what we can actually, on the bright edge of what we can actually observe. Another image, a very famous object here. This is Saturn, and I like this because we can also see some of the moons of Saturn, Mimas, Tethys, Enceladus, Dione, and Titan here, and Janus. And the rings, you can see some of the atmospheric, again, the colors here look nice, but they're actually telling us about the chemical makeup of what's going on deeper into the atmosphere of Saturn. And we've had infrared telescopes from the Earth that have looked in certain wavelength bands, and Hubble's done a little bit of this and other telescopes, but with JWST, you can do it in a new and unprecedented way. Here's another beautiful exploded star. This is the Crab Nebula, very, very famous supernova remnant. The supernova was observed in 1054 by scientists around the, scientists and people around the world. There's records of this in Chinese astronomy. There's records of this in Arabic astronomy. We think that the ancestral Pueblo Indians up in northern Arizona saw this star exploding and painted it on one of their walls. And when we look where all these people were looking, when we go to the Chinese records and look where they found this guest star, we see the exploded remnant, this Crab Nebula, which is the outer layers of a star after it has died, a very massive star, and it's exploded, leaving behind, and you can see right in here the Crab pulsar. So something like the size of Chicago spinning thousands of times every second. That is composed of heavy neutrons, like very dense neutrons, like the kind of the famous spoonful weighs a ton thing, just all spinning here, the remnant core, collapsed core of the supernova with all of this around. And this is important here because this gas cloud contains a lot of heavy elements. For instance, a heavy element you're very familiar with called oxygen. So again, right now you are breathing something that the way that the universe formed oxygen, and I'm not saying this like, oh, well, one of the ways. No, this is how the universe formed oxygen. To make oxygen, the stuff that you depend on to live, a star had to explode like this. And so you take a little bit of the oxygen from this, and that went into the formation of our solar system and what you just happen to use to breathe, what goes into the water you drink. It's kind of crazy to think about that, what the universe and how it built us. And again, at the end of the talk, I'll show that you'll come back to this, but I really want to show this while we're looking at this because we can use images from JWST, compare them to Hubble to watch as this thing evolves, to see the kinematics, so the motions of this thing over time, the velocities, how fast the light is moving, the gas is moving from this explosion. We can use this to, again, look through a lot of dust that's been formed to see this in a new way. Here is the Wolf-Rayet star APEP, which is actually two stars that are moving around each other. On a 25 years, they go around each other, and they make these shells as they move around, these big dust shells. And you can see shell, shell, shell. This is 25-year time scales of these two stars moving around each other. And that's important because dust is vital for our understanding of how chemicals come to be, how molecules come to be. If you think about atoms floating through the universe, how does atoms meet each other? How did a water molecule meet? How did the hydrogens and the oxygen meet? There's a lot of empty space. That's why we call it space, not outer stuff. We call it outer space because it's just big empty space. And so how is it that hydrogen and oxygen just happen to find each other? And the answer is likely that they were drawn by electromagnetic pull to dust grains. And on dust grains, the surface of dust grains, they met each other like a singles bar. And so dust, the history of dust in our universe is the history of molecules, the history of complexity. We owe probably our existence to dust grains coming together as part of things like comets and asteroids, bringing complexity down to a baby Earth. And we can watch that by looking at things like this, where because these are on a time scale where they kick out these big shells, we can look at the history of dust in this object. And we can model this in 3 dimensions, which is very exciting. I love this image. It's really wild. It looks like an embryo floating in it's really, like Arthur C. Clarke would have a field day with this. Here's a recent image right here that's showing, I can't see right down in the corner, it's FS Tau. And it's a protostar system. So there's actually 2 stars here and the 3rd star here. And it's a very similar thing where because of the fact that we are able to look through the dust, we can look at this very young star and see how it actually is impacting the gas that is still around it, has not been fully blown away from its young star birth right now. And we're actually able to see the formation of dust around these stars in something called polycyclic aromatic hydrocarbons, which is just big chains of carbon with oxygen on it, which is kind of like soot, space soot. And we actually can see that and trace that using the mid-infrared instrument MIRI. Here's another planetary nebula here, seen both with NIRCam and MIRI. It's called the Exposed Cranium Nebula because it kind of looks like, like we've got this open brain looking down, but it's actually just another planetary nebula, so another outer layers of a star that has died, like our sun, puffing off into space. And you're getting some dust, which is actually what's causing this cranial ridge here. But there's, multiple eras of the star puffing out its layers, which is what causes the different different things here. And then moving a little farther out, because we're going to get to my research in a little bit, but moving a little farther out, this is an image just from a couple months ago. This is M82, the Cigar Galaxy, but it is, I think of it as the starburst galaxy, and you're actually seeing with NIRCam here, through a lot of the dust that Hubble would show to see some of the stars and the younger stars here. But this red is an outflow, a stellar outflow. This star has so many stars being born right now that it is kicking those stars and their star formation and the star death, supernovas. They are pushing gas out. You get these big plumes of gas, this cone on either side, as the gas has a harder time moving in these directions because there's galaxy in the way. So instead, it's just making these fountains of gas on either side. And to give you a comparison of why JWST is a revolution for seeing through a lot of that dust that I'm talking about, here is a Hubble versus a JWST image of the same exact region. And if I showed you this, you might not be able to pick up on that, but you can actually see that there are some of the same stars that you're seeing in both of these, but it is a thing where, like this over here and this right there. This is the exact same thing, but over here, all this red is dust. Dust is blocking our ability to see the young stars and the stars that are forming this star-forming outflow. But over here, you're able to see all of these. There's so many stars that almost uncountable, right? It's really, really, this is entirely full of stars, but they look red because of the dust that's making them look red. And over here, you're actually able to see them, understand the populations. Believe me, there are people who, even if it doesn't look countable, they go to this and they use computer programs to just take and measure the brightness of every single one of the stars there, so they can look at a statistical synthesis of what the star formation is in these objects, how when the stars get born, how bright are they, what's the population, and do population models, something you cannot do here because of how much dust is obscuring what you want to see. So this is the type of thing JWST has done in its 4 years. In many ways, it has really lifted the cover on our understanding of how stars are born, how they grow, how stars affect the chemical makeup of the gas around them, leading to new generations of stars, how they live their lives and explode and die. It's been incredible for that. But I don't work on that. I work on distant galaxies. And so let's talk about distant galaxies. So the rest of this is going to talk about some of my research with distant galaxies. And to get us on the same page, I want to talk about the fact that really what I care about is not the distant galaxies, because the distant galaxies, if I could actually see them as they are right now, would just be a lot like the Milky Way and the galaxies that we see nearby. So I don't care really that they're far away. What I care about is that because the speed of light is finite, it takes time for light to go from an object to our eyes. So when I see the galaxies that I'm looking at, I'm not seeing them as they are right now. I'm seeing them as they were when the light left. This is a thing that some people, they go, oh yeah, this is obvious. But for some people, it's a weird mind trip. But you interact with this all the time, especially if you've ever sent a letter to someone. When you get a letter in the mail and you open it up, it's not what your friend was doing who sent the letter right now. It's what they were doing when they were writing the letter. Like hundreds of years ago, someone might send a letter from Europe. They'll have to go across the ocean, maybe across the country and get to you. And you read it, maybe it took a month to get it. You'd read, oh, I'm sitting and having tea right now. No, they're not having tea right now. They were having tea a month ago. You're seeing a time travel, oh, my friend a month ago was doing this. And for the stars and galaxies that I care about that are far away, the timeline is not a month. It's millions or billions of years in the past. So the reason I care about faraway galaxies is not that they're far away, it's that they're from the past. And they're showing us the history of the universe. And so as I look with JWST into the more distant universe, I'm looking at farther back in time than when the sun was formed to earlier and earlier periods stretching back towards the Big Bang. Which means I am a historian. This is going to be now transferring from a talk that is about like the history of the universe as opposed to, well, this is what's going on around us, which lets us understand how we came to be. No, we can actually see how galaxies grew and changed over time. Galaxies like the Milky Way, galaxies containing stars and gas and planets. And before JWST, two of the main ways with which we understood the early universe came from Hubble. So this right here is two very famous images. This is the Hubble Deep Field. This is the Hubble Ultra Deep Field. And these were regions. This is from 1986. This is the mid-2000s, things like 2004. 1986, around Christmas in 1986, Hubble opened up its shutter on a patch of sky that was relatively free of stars. So it was not looking in the plane of the Milky Way. It was looking at a region outside of the plane of the Milky Way to try and go, kind of near the Ursa Major, to go like, well, okay, if we open up the shutter, hopefully we will see lots and lots of galaxies. Now, this was something that some scientists thought, of course. And then there were scientists who were on the record as saying, Hubble will never discover any new galaxies that have not already been discovered. That was an actual quote by someone when Hubble was being prepared. And this was a test to see, is that true? Should we do this? And this was time that was not time from a proposal. It was director's discretionary time. The director of the Hubble Space Telescope at the time, Roger Williams, he was like, I'm going to use some of my time, get some scientists together. We're going to plan this really well and take this image. And in January of 1996, so in December 95, took the images in January 96. This was released as part of the American Astronomical Society's annual meeting, and it really caused a hubbub. This image right here, which represents a series of tiled images from Hubble's camera, just like the Wide Field Planetary Camera 2, completely revolutionized our understanding of the history of the universe, because everything in this image is a galaxy, except the ones with the little spikes. Those are stars. Everything else is a galaxy. Thousands of galaxies. Galaxies stretching back farther than we've ever seen. And years later, we assembled more time, and we pointed in an entirely different region, thinking, well, okay, maybe we just got lucky. Maybe we were looking at one patch that happened to be the patch with all the galaxies. Let's look at an entirely different region in the southern hemisphere. And we took this, which is the Hubble Ultra Deep Field. It was deeper, more filters, and different camera, multiple different cameras on board Hubble, and hammered away, and same thing, filled with galaxies. And the things that we learned from this applied to what we learned here, helping us understand that, yes, the universe isn't privileged if we look in one direction versus the other. In fact, if we were likely to point Hubble in any direction, as long as there wasn't some Milky Way thing in the way, you'd see galaxies like this. And JWST has helped confirm that, in that almost every image, I have people complaining to me because there's galaxies behind what they want to look at. All my friends who look at things in our Milky Way are like, your galaxies are so annoying, photobombing everything I want to look at. And I go, you should, as I joked earlier, stop taking pictures of galaxies with something in the way. These stars are the most annoying thing. I'm joking. We should be using telescopes to do all sorts of stuff. I showed you all those beautiful images. We should not just be looking at faraway things. These came out. I was 13, and then I was like 21. These came out and completely changed my life. Like these images. Like I am a person who grew up, and when you'd get to the flip to the back of the science books from my youth, I bet in some of these you'd find it, you'd see this image. And I just kept thinking, gosh, what's outside of these jagged lines? Like what's over here? What's over here? Like what are we missing? We're looking. It's like opening up this tiny little window. Like, gosh, I wish you could go farther and see more. And the thing is these images, I just had this idea of it looks like they're all in a plane, but they're not. We're looking back in time, right? So here's this graphic showing what I'm talking about, which is this is a different entire region. But every one of these objects can be assigned a distance, which we call its redshift. We'll get to that in a second. And this is like a window showing us galaxies stretching farther and farther back in time, right? 2 billion years ago, 4 billion years ago, 6 billion years ago, 8, 10 billion years ago. That's crazy to me to think about. Where does this end? How far back can we see? Where were the first galaxies? It seemed like, and more that I studied astronomy, Hubble was unfortunately limited in its ability to do that because of the wavelength of light that Hubble could see. Hubble is a telescope that has infrared instruments on it, but those infrared instruments stop at around 2.4 microns, which is near infrared. In fact, one of the main near infrared instruments that was first built, the camera NICMOS, was built here at University of Arizona by people at University of Arizona. And then it was succeeded by a camera called the Wide Field Planetary Camera, and 2 and 3. And they had instruments, go out to about 2.4 microns. And that 2.4 microns means that if you go even farther back in time, the light has been entirely from those galaxies has been shifted so that Hubble couldn't see it, which means you would really need to go farther, to look farther back in time to succeed at the edges of what Hubble could do, you need a camera in the infrared like NIRCam. And so, as a child, wondering what's on the outside, what's on the edges of those images, I was really thrilled when I got this job, because part of this job was that when you build a camera on board a space telescope, you are given a certain number of hours with which you can do whatever you want with. And Marcia donated 400 of her 800 hours towards a survey that we called JADES. And this is JADES. JADES is at this point, over 400 hours of imaging time across 2 fields, which we'll talk about in a second. And it's added to it 400 hours of spectroscopic time, which I'll come back into in a second. But it is, in fact, the successor to the Hubble Ultra Deep Field and Hubble Deep Field. And it is something that is probably I'm most proud about the JADES work as a member of the team. And I'm only showing you a small portion. This is zooming out here. And to show you that actually, this is the full JADES survey data, combining our own data and data from other teams that is public, that is in the same region. And to give you a comparison, the Hubble Ultra Deep Field that I showed you, this giant Hubble Ultra Deep Field with thousands and thousands of galaxies, the absolute revolutionary thing in the 2000s, all the way up to about to 2021 when JWST launched, that entire field is literally just that box right there. Same objects. So when I wondered what's on the outside, I now know. I can go pull out my phone and show you. And I will tell you, this is going to sound cocky, but I think it's true. I am probably the person on planet Earth who has looked at more galaxies in this field than any other person alive. Because I am the librarian of JADES. For every galaxy in the survey, I have made a fit showing it. I'm the person who figures out how far away they are. I'm the person that everyone in the team comes to if they find something weird. And generally, I've found it before them and have a page or some website or something. I love finding things in this survey. I love it. And we have an entire other field in the goods north, so in the northern hemisphere, which is also where the Hubble Deep Field was. So now exactly, I can literally take where the Hubble Deep Field was, and in that little corner up there, I can tell you exactly what galaxies they are. They're just these galaxies right here. It's really, really amazing how much data this represents. There are, gosh, almost, like there's probably more than 500,000 galaxies across the whole survey. It's really absurd. And you can see how annoying the stars are because they make all these spikes, But there's a reason why we observe this, because we want as limited stars as possible. I'm obviously not that angry about stars. So the thing about this is that I want to find the distances to the galaxies. That's what I do for a living. And to find distances to galaxies, I utilize the fact that the universe is expanding. So this looks like I'm zooming in. I'm just floating in space, and the universe is expanding. The galaxies are all moving away from every other galaxy. This is something Edwin Hubble found. And that has an impact by the fact that because everything's expanding, its light is actually being stretched to longer and longer wavelengths. And the farther something is away from us, the faster it's moving away from us because of how the expansion of the universe works. We're also expanding. The universe is expanding. Everything's moving away from everything else. It just doesn't feel like it because we don't feel our own motion to the universe. And so that means that we sit in the spot where, as we look to farther and farther things, we can actually say, the farther it is, the faster it's moving away from us, and therefore its light is stretched to longer wavelengths, which is something we call the redshift. So here is, a thing where if we were to take and pass the light from a galaxy through a prism, and then have it zoom away from us, all of the various these black lines, which are absorption or whatever, will be shifted to longer wavelengths. In the same way that when a car passes or a motorcycle, it's the engine pitch goes high pitch as it's coming towards you. And that lower pitch is the wavelength of sound being stretched from the Doppler shift. This is a Doppler shift for light. This is an annoying equation. It's a very simple equation. I said there would be no equations, but look, this is in case for the dorks in the audience who want to understand how to calculate redshift. You take the difference between where you see it and where you see it and where it is versus divided by where it is, and you get this number redshift. It's just a number. That number is not linear. It's a number that, here is essentially how far away the object is, and then how far back in time it is, which is more exciting for me in blue, versus redshift. So nearby, it's not any back in time, 0, right? But then as you move farther and farther at higher and higher redshift, this blue line here, you get farther and farther back in time. And then you're looking farther and farther away where that object would actually be over, if you look, as the universe is expanding. And notice that you get a really far back in time by going 0 to 4, right? You get like, almost 10, 12 billion years into the past. And then it's kind of diminishing returns here. But I still care quite a bit about the fact that, man, it'd be really great to see galaxies at these redshifts because we're still crawling back to the first couple 100 million years after the Big Bang. So the game is, if we can find the redshift of the galaxy, we can tell its distance using a graph like this, using these equations that go into the graph like this. All I just need is the redshift of the object. All I need is the pitch of the motorcycle as it's going by, because I know the pitch of the motorcycle if it's just idling in front of me. If I can tell that pitch, I can tell its velocity. If I can look at the difference between what I see the galaxy zooming away from us versus what I know it should be, if it were just sitting stationary, I could tell its distance away from us. And to do that, you need to take a spectrum. So this is a real galaxy in the survey with these little white boxes, which are the doors on NIRSpec. It's got these little slits that take the light, and you can use that to put it onto a prism. And then you can look at the light as a function of wavelength and take a spectrum. This is what a spectrum looks like of this galaxy. The actual raw spectrum. And these little blobs are from gas in the galaxy. And if you do this as much as I have, as much as many astronomers have, you can see these three specifically and go, aha, oxygen and hydrogen. This is oxygen gas, hydrogen gas. That means this is oxygen. Here's another oxygen line. And if I take this, and instead of showing it like this, I make a graph, like I cut through here and make these into spikes. So this is the exact same thing right down here. You can see the spike, the spike, the spikes, the spike. You can actually look and see all of this comes from the chemistry and stars being made up in the galaxy. But this oxygen, where it says OIII, which stands for oxygen 3, that should be in the green. About 5,007 angstroms in the green. This is one of the most important lines. My graduate student, Sophie Leibowitz, is graduating in 3 weeks as an expert on oxygen 3 in galaxies. At some point, I will actually do this, but I think that I need to make a tattoo appointment and get this tattooed on me. I have built my entire career about this oxygen gas. Like I see this right here, and just I can close my eyes and see oxygen 3. When it was first discovered, when scientists first discovered this, they didn't know what it was. There's like weird brackets around it because it cannot be seen on the Earth. So they called it nebulium. They thought, here's a new element, nebulium, in the universe, because you only see it in nebulae. And then eventually some scientists were like, actually, no, it's doubly ionized oxygen. It's just in a very specific state that only can be seen out in the universe where it's so tenuous that you can't ruin it by having other atoms crash into it like you would here on our planet. Oxygen gas at 5007, that's what this rest is. We're actually seeing it about 3.5 microns, 3.7, 3.8 microns. And if I take the difference there, I get the redshift of the galaxy. And so this is what you could do. But taking spectra is really time consuming. So instead, I utilize this cliff. Do you see this cliff that says LY and then an alpha? That stands for Lyman alpha. The fact that all of the light suddenly like stops right there where it has this shutter thing. It goes like, and there's a cliff. That cliff comes from the fact that this galaxy is filled with hydrogen gas. And the hydrogen gas is absorbing all of the light over here. So if I look here, here is a synthetic model galaxy where you're seeing the same thing. There's the oxygen, there's the hydrogen, same thing as the last one. And then it hits this cliff. If I take pictures at different wavelengths, like a Hubble picture at 0.6 microns, which is about here, at 0.8 microns, which is here, 0.9, which is that box, each one of these, I would see the galaxy, and then I wouldn't, because hydrogen gas is absorbing all the light. And as I push this galaxy to higher redshift, the whole spectrum gets shifted to longer and longer wavelengths. So watch. The fact that I can tell that this right here is not seen and then suddenly it's seen makes this object what we call an F606W dropout. It's dropped out of this. And as I go to higher redshift, which is earlier in the history of the universe, it drops out of each filter. And that tells me the distance to the galaxy. That gives me a rough estimate of the distance to the galaxy. This right here would be an F200 dropout, which would be at an unprecedented redshift of 17, which is only 225 million years after the Big Bang. So this is synthetic. In JADES, I found a bunch of galaxies that did that. Boom. Look at this. These are real galaxies. Every one of these is a real galaxy in the survey where it has dropped out of FO90. It's dropped out of FO90 and F115, and I see it in all these other filters. It's dropped out of FO90, 115, and 150, and I see it. And it gives me a rough estimate of its redshift. I'm able to see, if I could take a spectrum of this object, it would go up and up and up and up and then drop right here, and that tells me the redshift. And I did that for the entire survey, and I put it in a paper earlier this year with our final data set and our final survey. And this is the conclusion. These are the 2,000 farthest over 2,000 farthest galaxies across the entire survey. Over 2,000. Every dot is a galaxy that I have looked at by eye, painstakingly, weeding out all of the interlopers to try and find these objects. Now, I call them mostly candidates because we don't know for many of them. The ones that have a white circle around them, we do have a confirmation. They are, in fact, at the redshift distances that I predicted them. And you can see how limited we were in our ability to see. There's some really far away galaxies in these boxes, the Hubble Ultra Deep Field and the Hubble Deep Field. But man, they're all over the place, just outside, some of the farthest ones. This right here was probably a paper that was the culmination of my entire career when I submitted it later this year. And what's exciting is it forms the basis of not just my follow-up observations and follow-up observations from the JADES team, but scientists around the world have been following these up. They trust my observations, they trust my analysis, and they're going after these to be like, oh man. We found these galaxies are not just little smudges like the ones I just showed you. Here are actual galaxies. I've given them names. We're technically not supposed to give them names, so don't quote me on the names, but I like to call them names just because it helps me, because when you see enough galaxies, you start to, This one right here, I should say, I mentioned this to a reporter for Nature, and she called this the glowing dog bone in her article, so now it's official. But it looks like two clumps. This one's multiple clumps that I think that we will call the poodle in the paper. You can see the little head of the poodle, the tail, the little front and back legs. It's very well manicured. This looks like a croissant with these three clumps. These galaxies are seen in the first 500 million years after the Big Bang. This is incredible because you only have 500 million years with which to create enormous clumps of stars in baby-forming galaxies. The boomerang here. These two, notice I haven't put white. This is actually how far away they are on the sky from each other. The distance, if you put the center of the Milky Way here, the Earth would be over here. 8 kiloparsecs separates them. It's really crazy how we're actually able, with JWST for the first time, to watch galaxies in the process of forming complexity. This galaxy right here was a galaxy that was first discovered, and we took a spectrum of it. I showed this spectrum at a meeting, a scientific meeting, and had multiple scientists tell me this was incorrect, this was a mistake, you should not be able to see this. Remember how I told you that the universe, like these galaxies, have that cliff because of the hydrogen around them? Here's the cliff. You see the cliff, cliff, right? It's hard to see, but it's seen right there, cliff. But this spike right here, that spike is hydrogen gas that is glowing like a lighthouse. That you should not be able to see this at this redshift. You should not. The universe should be completely opaque to this. This galaxy must have inflated some sort of enormous bubble around it. All of those baby stars have made such an enormous bubble that it allows this specific lighthouse of hydrogen emission to fly through, this Lyman alpha at redshift 13. This galaxy was part of a Nature article written by Joris Wittstock that I Oh yeah, I don't know why I muted. Hopefully you can hear me now. That's weird. Okay, sorry about that, folks. I didn't know. This right here represents, as far as I can, maybe there's probably some other ones, but this is the redshifts of the objects and how far back in the past we're looking. So time since the Big Bang, 0 would be infinitely over on the right because redshift doesn't work that way. But you're seeing all of these galaxies in gray are my sample, mostly candidates because we don't know if they are at the distances they're predicted. But the ones with the big circles and names are in fact the galaxies we have confirmed. And this right here is how bright they are intrinsically, the absolute magnitude. And so GNZ11, which was Hubble's farthest galaxy, it was very, very bright. And it was seen at around a redshift 10.6, which is 450, 440 million years after the Big Bang. And we're now pushing back to within the first 300 million years. So you're seeing right here how far back we are starting to actually go. I have some candidates that would be a little bit farther, but we'd have to go. They're very intrinsically faint. We'd have to go find them. But it's really showing us how the universe changed. The reason why we care about this is we're seeing how the universe changed from the Big Bang to today. This is a diagram that I helped make for National Geographic. I was very excited in a special space issue where we're seeing all of this, the Big Bang, a period of the universe being entirely foggy and opaque to radiation, and then the first stars and galaxy clearing out the universe in its opacity to start making a clear universe, clearing and completed with the first spiral galaxies as we move on. And I'm only showing the first 1.5 billion years, but this right here is, we're peering into this region of the first stars and galaxies with GSC14, with MOM-Z14, Pano-Z14, with these really, really distant galaxies. And I think that one of the things to look out for over the next 5 years is the maturity of our understanding of these galaxies. Because right now there's so few, And it matters because by looking at galaxies in this region, we're seeing them as they become more and more pristine. The galaxies like, JADES GSC14 is exciting because it has evidence, multiple ways, of oxygen gas. We've seen it through multiple different telescopes of oxygen gas. And it's only 300 million years after the Big Bang. So there must have been stars that lived and had explosions and gave up enormous amounts of oxygen gas on only 300 million years after the universe began. If the universe were a 2-hour movie, 300 million years in would be like the first 2 minutes. So like if the universe were Star Wars, we're seeing JADES GSC14 as it is when we first meet C-3PO. So that, like, imagine, the stars living and dying in those first 2 minutes are like those rebel troopers that get killed by the stormtroopers within like the first couple minutes of the movie. Like that's exactly what we're seeing, is that stars had to live their entire lives and die in enormous explosions, giving up their complexity to make this oxygen gas in only 300 million years. And that matters because of this. This is the periodic table of the elements, which is also up there. But I've colored these, or the person who made this has colored these by what we think their cosmic origin is. And this diagram, the fact that we can know what these elements are and how the universe built them, that is a triumph of astronomy that JWST in its first 4 years has given us multiple ways in. This is what I've kind of been building to by hinting at this the whole talk. But we can see the things like the dying low mass stars, the exploding white dwarfs and exploding massive stars, because the Big Bang only made hydrogen, helium, a tiny bit of lithium here. Everything else was formed through stars being born and dying in enormous explosions or in neutron stars merging. And this is something we can actually see by tracing this out in the history of galaxies. So earlier this year, we made all of the JADES data public. Don't do it right now, but on your own time. You can go to this website here, jades-survey.github.io, and you can look at, there's like a thing that says viewer. You could just go look at all of JADES like it's Google Maps. Zoom in, zoom out. Up in the corner, there's a little box. If you put on the box, this lower one, you can put a little circle on every galaxy and click on the galaxy and look at its spectral energy distribution, my predicted distance. You can start having fun. In fact, since doing this, we've had this public for years now, but the final version's only been a number of months. I get people emailing me with like, what's this? What's going on here? What's this? And it's really fun to do that because generally I've seen it before. And the answer is almost entirely it's a brown dwarf or it's one of those little red dots, those young growing supermassive black holes. Because that's what people really get excited about because they look like really fun little pinpricks. But there's lots of fun stuff to look at here. You can go find GSC14. For those watching at home who are already on it, if you go to the Good South and look up 183348, that's the ID number for GSC 14. But it's a really exciting thing. And if you like hearing me talk, if you think, man, that guy's got an interesting way of talking, and want to see me again, I'm going to use this as a promotion. Sorry if you don't want me to use it as a promotion. But next week, I will be at Flangel Planetarium on July 10th and 11th with a show that I've written with my wife, Lara Ruggles, who's a musician. It's my speaking. It's her with a band, musical, entirely, like there's a whole musical accompaniment and the visuals over top. It's an amazing show that is called You Were Light. We've actually recorded it to vinyl as well. Like, we're really, really proud of this show. It's very different than the scientific, discussion here. It's a lot about our shared cosmic origins, as I say here, and you get a full concert throughout it as well. And I urge you, if you're interested in going and have a free night. The problem is that July 10th is already sold out. So I apologize, but you're going to have to go on the 11th, unless you already have a ticket to there. But please come. It's at 6:30. Your ticket also allows you to go see the new exhibits there, and there's another planetarium show. It's going to be a wonderful night. Please, please, please come. I think there's maybe less than 50 tickets left right now, and I absolutely love this show. It is a wonderful, wonderful thing. And even if you just go to kind of zone out and look at the beautiful visuals and hear my wife singing, she's written new songs for it. It's very special. It's called You Were Light. You can look it up on the Flangel website. And I would love it if you all bought tickets and came next week. So I'm going to finish there and answer questions you might have. Thank you all very much. I'm excited for the future of JWST. And I'll make sure to take questions from the audience as well. The Zoom audience, I mean, sorry.
If you have a question, wait for us to bring you the microphone so that
Here's the
those
second
online
mic
can
if you'd
hear
like
you.
to-
Yeah, I haven't ever seen this. What is the actual field of view of the NIRCam?
So NIRCam has two cameras that are 2.2 by 2.2 arc minutes, or two, yeah, so it's like 2.2 by 4, so yeah, 2 by 4 arc minutes.
Okay, and how's that compare to Hubble then? It's
Hubble's ACS and WIFC3 had different camera fields of view, but generally one of the WIFC3 fields of view was smaller than one half of NIRCam, so like 2 arc minutes by 2 arc minutes.
and the mid-range camera has the same field of view, or
The MIRI's camera is a lot smaller because MIRI it has to be actively cooled. MIRI is a complicated camera, so its field of view is significantly smaller than one NIRCam thing. And that's why MIRI is not a great camera for survey work. You're not going to take giant chunks and stitch them together. It's good for targeted follow-up as well. But you can actually go to you can go to our FITSMAP, our viewer, and see that we have a big chunk that is part of a survey with MIRI that has been used in that way, but it's not the most efficient thing to do with MIRI because it really is a small field of view.
thank you.
You're welcome. Good question. Yes. Oh, microphone's coming. I appreciate the microphone runners. Yep. Is this not working? Oh, no. Oh, well, I will take tricked into thinking it will work. So yeah, hand the microphone over to this gentleman. Sorry about that.
I noticed that you've been using synthetic photometric, for your system and that. Is there a reason why you're not using the Johnson photometrics, or is it, I got that wrong with it?
So when it comes to photometry, all right. So the Johnson system, UVBRI, those filters were built for ground-based telescopes, and they're optical, right? UVBRI. And I is where you get I don't even know, I is like just barely near infrared. With NIRCam, we have specific filters that are wide, medium, and then there's narrow filters that were designed for the usage with the camera and the sensitivity of the detectors in the near infrared and near infrared, and they need to be characterized really, really well, and they have to have very specific bandwidths because of the science, what we want to do with that. So the filters that we're using, if I go back over to something like this, these filters UVBRI would be off to the, there's not like there are standard Y, H, J, and K filters in the near infrared.
You're talking about for the Johnson ones, not Pacific.
Yeah, there are near infrared filters but they are designed to sit in atmospheric windows on the Earth. And because we don't have to worry about Earth atmosphere, we can make filters that are specifically designed to cover the entirety of the NIRCam like wavelength range and be well characterized and work well with the quantum efficiency of the detector itself. So these filters are different than what's on Hubble. Hubble has a different quantum efficiency of its detectors. They are designed for NIRCam specifically, and like I said, NIRIS, which works in the same way. These are just a small fraction, not a small fraction, but these are the wide filters. There's a bunch of narrow filters, and there's also medium band filters as well. You can see this is a medium one, the M versus the W, but they're for NIRCam specifically. And mostly like UVBRI are standardized for ground-based astronomers because it's easier for them to make those filters, and they work well with a wide variety of the detectors that you have when you buy them for here on the planet.
I understand now.
Yeah. Yeah. Thank you. Other questions? These are good questions. I love answering questions that I know the answers to. In the back.
You mentioned the quantum efficiency. What is the quantum efficiency of the cameras? Do you?
There's not like a number I can tell you. It's not like 5 or whatever. It's like you can go and look on the website JDocs for our measurement of essentially, because what you really want when you do this is when JWST, so NIRCam, the detectors aren't CCDs. They are an infrared detector that is an infrared crystal called a mercury cadmium telluride crystal. And the way that it takes infrared light and turns it into electrical signals, that is what I'm talking about. And that's a thing where you can go look that up. NIRCam's also kind of clever. Infrared cameras are clever in that you don't, like with a CCD on our planet, you open your shutter, you will get your information when you close the shutter or whatever, and you essentially say, okay, how many photons or how much electrical signal did you get at each pixel? But NIRCam can sample non-destructively, which means that I can sample over time, and you get what's called a ramp. So your images are actually enormous. You get this, like, for every pixel, you get a ramp, and you're actually fitting a straight line to that ramp because you're assuming the light is coming down to that pixel, and it's just increasing linearly over time, which it generally is. And so you called sampling up the ramp, and you have to pick when you choose how to observe, pick your sampling rate and how, because the more samples you do, the bigger the data is, the less data you can take. You sample, maybe you'll sample at the beginning and sample at the end and fit a straight line to that, and that ramp is what you get. You get the ramps down from the telescope. But all that is to say is that to do that effectively, you need to know the quantum efficiency. And so all that's built into our pipeline, but you can also look up this information on the JDocs website. And there's so much. Like if I show this image, let's go just down here. Like these mosaics are so much man effort, so much person effort, I should say. They're so much human effort because the data, when it comes down raw from the telescope, is in a state that like you have to remove so much and then stack all of these little stacks of the images. If I go back to the JADES, yeah. So do you see that like there are some boxes down here? These are some parallel data, but like this is one chip. This is one NIRCam field of view, and then another NIRCam field of view. So this is the rectangle that I was talking about. And so imagine the whole thing is comprised of that, stacked together. And as you know, maybe you don't, but some of you probably know, there's aberrations at the edges of your detectors. So if you try and take 2 images, if you move your telescope and take another image and try and stack, if you don't account for that aberration, the stars on the edge will not line up. And you have to account for that perfectly here. And we have to align this to an underlying frame this Space Telescope Gaia helps us do that, and account for the astronomy, like the distortion, and account for the fact that there's different, like, you know, and do this for all the filters, and remove the fact that this is such a sensitive camera that anytime there was like a star or something that glinted in, that like was off the field but reflected on some stupid piece of JWST onto the detector in some way, it would cause a tiny little glint that you'd have to remove that out. This is a non-trivial, complicated piece of scientific, data reduction analysis that starts with this thing, this question you asked, which is, what's the quantum efficiency? That's just the start. That's just saying, well, all right, if I get an infrared photon flying through the universe and it hits the detector, what's the likelihood of it kicking off an electron that I can detect? And then from there, you have to go many, many hours to try and turn this into data for science to be done. And now you can just look at it through Google Maps. It's insane. It's crazy. Like this data, if you wanted to, you can just go right now on your computer to our website and just download the whole catalog, the reduced catalog, and just go, good, I'll skip all the hard part and just go directly to every single object. And I've even given you the distances, the guesses of the distances. It's just, we've done a lot of work for the scientific community. Other questions? Is there any online should I be looking at? I don't know if someone is monitoring the chat.
Bob,
Oh,
is there anybody online?
We have one here in the back.
I will answer those. I see the ones that are online, but I'm going to answer this one in the back. Yes.
Thank you for the presentation. While measuring the distant galaxies' brightness, how do you optimize the other objects contributing to actual galaxy brightness? Because while looking at distant galaxies, since the difference between the other objects is getting so much smaller, there is going to be other light that is going to be distract this actual brightness of the galaxy. So how do you actually differentiate those lights from the actual galaxies, its full brightness?
We're actually pretty lucky that generally outside of things like this, where this galaxy is in fact kind of blocking it, generally the galaxies aren't like getting in front of each other too much. There is some of that, and it's kind of annoying in certain ways, but often we're zooming in so much. We have such a good zoom in on this and the resolution that we can separate the galaxies and figure out what's the light coming from one. Now, for some, if they are near a bright object, I wonder if I have any pictures that like if I do this, like there are some where the galaxies are like this brighter one. Like if it's really close to that, you'd have to watch out for a galaxy that's kind of close to this. But generally, you can separate them out in this exact way. Like the way that they made this was they just took every galaxy and they just said, okay, I'm going to just put that and put that, and then just like we just fly through the image, but they put it in 3 dimensions so that we could do this, because there's not a lot of blocking, and that's called confusion in astronomy. And if your resolution is not very good, you get a lot more confusion because your objects are smeared out more, and then you have to watch out. But with JWST, the camera is at a resolution that we're not confusion limited, which is what we call. We're actually able to kind of see the galaxies individually. And then we can use their predicted distances or their actual confirmed distances to figure out how bright they are intrinsically and how bright they should be, because they look fainter to us, but that's just because they're farther away. So I'm going to answer the questions online really quickly. One person asked the expected lifespan of JW. It's limited by the amount of fuel. The French corporation Arianespace launched the telescope so well that we're likely going to have about 20 years of JWST, hopefully, knock on wood. Unless something catastrophic happens. That is the fuel lifetime, and everything's been going exactly as was predicted in terms of the number of micrometeorites that we've expected and stuff. So I'm hoping for 20 plus years of lifetime for JWST, especially because at some point, I'll get proposals accepted. I'm joking. I've had proposals accepted, but it's someone also asked about little red dots, and I don't have time to talk about that, but I encourage you to search for my name, especially if you're at home, you can do that. I did a whole lecture at Space Telescope online about little red dots, and that's a whole other thing. You can look up Kevin Hainline, little red dots. You'll both find my paper on the subject, but also the whole video for the public on YouTube that has but little red dots, you have to invite me out for an entire other separate talk. They are mysterious they look like, when we look across our survey, they just look like little pimples, like red pimples. I don't know if I should put one in here, like, and we find them all over the place in JWST images across all fields. And it turns out that at first we were very confused by them. Now we have a better handle, but they still elude some of our understanding. We think they're likely black holes growing in the early universe in a weird way, maybe shrouded by gas, but they are something that we know that black holes exist in supermassive forms in galaxies all over the place. This is a way for us to see them growing in a really unique environment. Very exciting. And then someone else asked, can you share some observation you have seen or measured that was mind-boggling wow moment? And I thought I did. This right here, this was probably one of the most exciting moments of my career, seeing this spectrum for the first time and seeing that we had actually broken a record, not just with, I kept expecting more of the distant galaxies to look like weird little smudges, but to see something so bright, like I'm really like, this is the intrinsic brightness of the galaxies, right? And GSE 14, Pansy 14.1, these galaxies are like intrinsically like incredibly, incredibly bright. We're seeing an evolution of a class of galaxies that's very rare. Most of the galaxies that I have, the underlying ones, they're intrinsically more faint. It's really rare to get galaxies like this. And this galaxy, GSE 14, if we let it evolve, it might end up being brighter than GNC 14, which is GNC 11. It's like really, really crazy to think about how these things, they're going to get bigger and brighter. And that's at a certain point, how are they, what do these evolve into? Because we don't see anything that like is this bright in, as we go farther in time. So where are these galaxies that these types of things evolve into? And that's a wow moment for me. All right, there's another question here. Great. Yeah, I think I've gotten the ones that are online. Oh,
Yes.
no, there's another one. Yes.
Theoretically, you're going back and back. Is there a point at which the light wouldn't escape at all and therefore you couldn't see it? And approximately where do you think that,
Yeah, so this clearing begins as 400,000 years after the Big Bang. We've already seen it. It's part of your television static on old TVs. It's the cosmic microwave background. It was discovered in the 60s, won a Nobel Prize. And that is the farthest that we could possibly see, because before then, the universe is entirely opaque to radiation. All the radiation would bounce off of electrons.
Okay.
But what
So
we're
that's the
seeing,
theoretical limit, the cosmic background.
yes, but we are seeing galaxies, so 400,000 years to currently about 300 million years. I don't know what the farthest is. There are some people who've claimed to see galaxies redshift 30. Those are likely just brown dwarfs, not actually distant galaxies. Those are likely things that can trick you. But I think that over the next 5 to 10 years, that's going to be one of the big questions: is how far back do we actually start seeing these first stars and galaxies? And I'm thinking we are going to be, the next round will probably be redshift 16 objects, maybe 20 in the lifetime of JWST, but it's
Do
tough.
you think you'll need another specialized instrument to catch those first objects?
First stars, we can't see with JWST. We could potentially see their supernovae if they're bright enough, but not the actual stars themselves. We would need a way, way larger telescope. And I mean, good luck with America. Our current scientific funding is not, I should watch out with what I say. Our current government, it's going great for the sciences. But yes, we would need a larger telescope with a little more sensitive instruments. And I think that that's a nice chase, but I don't know if that's as exciting to me as what we were able to do, from between here on out. Another, JWST should be able to see galaxies about redshift 30 with its wavelength range. The problem is sensitivity. Another question? I've got a question online here also.
Go ahead. And take
Yeah,
it.
has JWST imaged supernova for the most distant galaxies? And the answer is not the most distant galaxies, because it tends to be pretty difficult, as we were just saying. But when you have data like this, because of the fact, why am I not finding that immediately? Yeah. Because of the fact that this data was taken over time in multiple rounds, multiple years, and most of this data has Hubble observations, we can look at differences between the JWST data and the Hubble data, or the JWST data and the data taken a year later or 2 years later, to look and see if we see any supernova or any transient events changing things. And Krista DeCourcy here, working with Ichi Igami here, she's a graduate student who's going to defend her thesis in 3 weeks. the day before my graduate student defends her thesis. She is the person who led the effort to look for the transient events and found supernova stretching back to galaxies we think at about a redshift of 5. So we're seeing them, it's not the earliest galaxies, but it's pretty darn close. Redshift 5 here is still putting us within the first couple hundred, like 500, 600 million years after the Big Bang, right? Like, and that's a very exciting thing to see supernova explosions in galaxies that early on. So we have seen them. It's really tough because you only have a couple, like one observation of it, and then one observation where it isn't in the galaxy, and then also associating some of these things with the galaxy is tough. But she's done a really good job characterizing these objects. Okay, anything else? I'm running out of gas myself. Is there one more thing?
Okay, yeah, there's 2 questions from YouTube.
Okay.
One, it says, I remember there being a docking adapter in the original design. Is that still there?
No.
And if so, could it be used?
Yeah, we did not create JWST for it to be fixable or docked. There's not like a docking adapter or anything like that. We'd have to be very, very clever. And again, it's 1,000,000 miles. It's 4 times farther than the moon, right? So we got real excited to send astronauts around the moon with Artemis 2. Getting out to JWST would be an incredible endeavor that would require, like, it put people very, very, very far away, or we'd have to do it robotically, and that would be also very tough. I really don't think, I think that the amount of money, like I'm very excited that we're currently thinking about how we're going to push the Swift telescope back up into orbit, and I'm hoping we do the same for Hubble. But right now, and again, I don't want to get in too much trouble, but like the American funding for the sciences is not in the best best state that it's ever been. And funding that, I don't see it as very likely right now for saving JWST at the time that it just runs out of fuel. So, but there's not a way in which we'd have to really, really devote a lot of time and effort to figuring that out.
Okay, and the last question seems very appropriate. What's the next goal for your work? Is it to keep looking for older and older objects?
So I think that's an aspect of it, is finding and confirming, right? Like I keep showing this diagram, and they've got all thee gray points. Every one of these gray dots, we could get a spectrum for and see how good Kevin is, right? Like how, they're just guesses. I am most of the dots with the circle, or the blue ones, those are my, I've discovered these ones. I didn't discover that, but most of these ones I discovered, and we confirmed as part of the work that JADES did. But I would love to be able to look at some of these objects and see how confident I could be and maybe break the record again. That'd be nice. But I think that I keep talking about a mature approach, is that chasing after the first one's really exciting, but we've kind of skipped the fact that there's a huge amount of information we can learn here. And one thing I'm working on right now is when we discovered that lighthouse, this object here, and found, not this object, when we discovered that lighthouse, this object here, with this Lyman alpha, I think we can do this in a lot of galaxies just from imaging, and I'm writing a paper on that. I also, and this is another entire talk, I am the world expert on finding brown dwarfs in this data, these failed stars at the edge of the Milky Way, and they tell us a huge amount about the history of the Milky Way, and that's something that I've been really, really excited about. And then I'm writing a paper right now on white dwarf discovery in this as well. I think that we need to get ready for the fact that over the next 10 years, we are going to be in a deluge of data with the Roman Space Telescope, with Rubin down in South America. It is just going to be data forever, and figuring out how to sift through that data and come up with correct inferences instead of just throwing it at a large, like an AI model or something like that, to do it in an intelligent way with human intelligence. That's going to be a really important thing. And so I am using what we're learning from JWST to help inform future explorations of these data, because as the librarian of JADES, I really, really want to make sure that people look at these data in a thoughtful, intelligent way, as opposed to just going, well, I'll just believe what ChatGPT says about it. All right. Well, thank you very much.
Thank you so much.
I hope to see some of you. You were late next week. It's going to be such a fun show. Please come if you're free on Saturday the 11th. Yeah.
All right. He's running out of steam. I didn't notice it, but he claims that he's running out of steam. But we're going to yank him off the stage. Thank you so much for your talk. We're going to come a little closer to Earth. Dr. Kokoschka, could you come up and give us the planet report? Eric comes and gives his report to us at the meeting each month. He also publishes on the website the report of the planets. So you can refer to that during the month. Oh.
In June, we had a really nice conjunction between Venus and Jupiter in the evening sky, where the two brightest planets came close to each other. But Jupiter is getting close to the sun, and in a week, it won't be visible in the west anymore. Venus is at its best right now. It's about as obvious as it will be in July, and then it goes in front of the, not exactly in front of the sun, but very close to it in October. So now it's about as obvious as it is in the evening sky. On the 9th, it's passing Regulus, which is close to the ecliptic, and it sets now at 10 p.m., so it's visible a fair number of hours in the evening. Then once Venus sets, there is no planet in the sky until Saturn rises around midnight. And the rings now in July are maximum for the year, for this year, and they are 11 times as open as they were at the beginning of the year. So they opened a lot because they were very thin at the beginning of the year, and for the rest of the year they close a little bit, but not too much. Then a little bit after Saturn, Mars rises around 2:30 a.m. It's in the Hyades star cluster, just in the northern part of it, and it wanders slowly towards the east. And Uranus is not a good planet to observe because it's low in the morning sky, but tomorrow morning it's only 7 arc minutes from Mars. And so if you can find Mars in the sky and you have binoculars, then you'll see a little dot right next to it, which may look like a moon of Mars, but it's actually something that's 10 times as far as Mars. And so that would be around 4 a.m. when you would be able such a close conjunctions. Such close conjunctions happen once every few years. And Mercury isn't visible for most of the month, but on the 27th, it starts a morning apparition where it's visible around 5 a.m. And that goes well into August. The moon is passing Mars on the 11th, and that's for the morning sky. So then we have new moon on the 14th, and just the next day, the 15th of July, there will be a really nice thin crescent. Then the following day on the 16th, it passes Regulus. This next day, 17th, it passes Venus. And then finally, a week later, on the 24th, it passes Antares. That's for the planets. The meteor shower in August are the Perseids. That's the major meteor shower we have. And since the meeting is, I think, on the 7th, the Perseids already started the end of July. So within end of July, early August, you can watching for the best meteor shower. Thank you.
Thank you, Eric. All right, I appreciate all those who've joined us on social media. It's time to close the meeting for those visitors. We're going to move on to some TAAA club business. Are we? We're moving on. Okay, we have a very exciting event.